All right, physics. So here is the second lab, the other lab, right, that we did collected data for during class. Um, and I'll just give you a little, like, explanation as to what it is, because I've just titled it, as you can see, like, conservation of momentum, and, like, true, yes. What we did, I took the class outside, had a couple of tennis rackets. Sorry, my phone is buzzing. Um, but took the class outside, a couple of tennis rackets, some tennis balls, and hit the ball back and forth, right? And each time that there's a collision between the racket and the ball, right, you should have conservation of momentum within reason, right? Perfect world, ideal situation where all we're looking at is racket and ball. It should be conserved. However, real life conditions will tell us that conservation was not, it looks like it was broken. Um, the primary reason it's going to look like it was broken is because I only asked y'all to look at the momentum in the x direction, right? So I only looked at horizontal, but we know that the ball and the racket both have some vertical motion up or down. So there is more conservation of momentum than appears here. Um, and your numbers may be a little skewed based on a number of other factors. But those are things that we can talk about, or y'all can talk about in the analysis, and I'll give you a little guidance on like what could have gone wrong or what factors could have contributed to this, right? Ultimately, you will type this up. Materials were just tennis rackets and tennis ball. Apparatus is just two people hitting the ball back and forth. And then the procedure was to, specifically what we looked at was a serve from myself and from a student, and a normal hit, right, a ground stroke. So a forehand hit or a hand hit, again, from myself and from a student. So there are 4 total collisions that we're looking at. Because we know momentum isn't completely conserved, what I'm interested in is what percentage, how much of the momentum, how much of this horizontal momentum is actually conserved. Based on the numbers, based on the graphs, you will have some results, and you should be able to explain why. I've already given you one little insight, the fact that we're only looking at horizontal and not the total momentum, right? There's also vertical momentum. So technically there's also some like depth momentum, right? Some z-axis momentum, but that's for a different physics class, not for ours. What you will need is obviously some data, so you'll need some graphs. Now the graphs look a little messier than the last one. Right? The last graph was kind of nice and straightforward. It had a couple of, well, it had a line and then a curve. This one is significantly messier, and you'll notice that they're all kind of messy. Now, obviously, Kalimlim is me, so this was the serve that I did. This was a forehand that I did. This is a serve that Lily hit, and this is a backhand that Lily hit. Now, it looks messy, right? But I'm going to, give you a little guidance, give you how to interpret this, how to look at this, right? So you should see red dots here, and they go up this way. And then you should see green dots here, and they kind of go up like that. The red dots represent the motion, the physical motion of the ball, so in the x direction, and the green dots represent the physical motion of the racket in the x direction. Right. Same here. Red is the ball in and leaving. Green is the racket, pretty much always going the same way. And then here again, red is the ball, green is the racket. Here, this kind of like orange-ish is the ball, and these pinkish purple are the racket. So in order to interpret this, right, it's a position time graph, and if you look at each of these boxes, they all say that it's some kind of linear fit. Linear fit for video analysis X, which was the ball. Linear fit for video analysis X2, which was the racket. Gives you that y equals mx plus b format again, and it tells you the slope, gives you units of meters per second, which means that the slope is the velocity. That should kind of make sense. The slope of a position time graph, position divided by time, that gives you velocity. You should also notice that some of the velocities, not on this graph, oh, wrong way, but here you have a negative velocity. Remember that only means that it's going backwards. It's going to the left in our case. To the right would be positive, so here's a positive slope. Now, again, I told you I would give you some information on how to interpret this, right? So each of these boxes points to a line, and each of those lines represents either the ball moving before the collision, the racket moving before the collision, the ball moving after the collision, or the racket moving after the collision. Now, I think that this person was very consistent. They always did the ball first, so anytime it's just X, the video analysis for X, that's the ball. I was going to make sure of that. Yes. Okay, so every time this person did the analysis, every time this person did the analysis, the X numbers, the X points represent the ball, the X2 points represent the racket, right? Now, if I look at this line, this box is pointing to this set of dots, and you can kind of tell it's a little more clear based on the ball. The ball looks like it's not moving, and then it suddenly moves, and this was a serve. And the reason it's not moving and suddenly moves, when I toss the ball, I should be tossing it straight up, and then the moment I hit it, it should fly out towards the other court. So it should have almost no horizontal velocity to start, and then lots of horizontal velocity after the collision. So my collision takes place kind of right here. And you can see the slope here is very small, 0.1034 meters per second, right? So pretty close to zero. And then if I look for video analysis X afterwards, it's moving 27 meters per second-ish, allegedly. Right, that's based on how we place down the points. So here is my ball before. This is my racket before, right? It's analyzing X2. And if I look, so here is the racket before the collision, and here is the racket after the collision. So those are the numbers to interpret, and that's how to interpret each of these graphs, right? If I were to look at the next one, I would see that this is video analysis X. So again, we established that's the ball. Excuse me, that's the ball. It's pointing to this best fit line. This looks like the ball coming in. Here's the collision. There's the point at which the ball changes direction, so that must be where the ball was hit by the racket. And again, for the racket, you can see that here is the before. This is before the collision. This is after the collision. The reason the racket seems to stay in place is because after the hit, after a follow-through, you hold the racket, so it stops. Or horizontally it stops, right? Now, there was one here. Okay, so for this one, the student did not do a linear fit for the ball horizontally here. What we can presume is that this section for the ball is probably very similar to this section for the ball. So you can do one of two things. One, for Lily serve, right? For the Lily serve, for the ball before, you can use the same velocity as the Kalimlim serve, or you can use a velocity of 0. For you can take it as an ideal situation. I'd recommend using the same velocity as the Kalimlim serve. Now, this gives you velocities. However, you will also need, and it occurs to me, I'll write something here. If my whiteboard app ever decides to show up. There it is. That is chemistry, which you are not interested in. Actually, I should make a new one. Let's just make a new one. Okay. So, something that you will... Or it can crash. And that's pretty cool, too. It's fine. Excuse me. Okay. So, something that y'all will want to look at is how am I going to turn these velocities into a momentum, right? What we need to look at is conservation of momentum, which is supposed to say, there we go. I think I can use a slightly larger size pen. So it's supposed to say that momentum before should equal the momentum after, P for momentum, right? Additionally, we know that P, that's a B. I'm trying to make a B. P equals m times v, mass times velocity. So we have the velocities from the graph, but I want to show you kind of like the calculation that you're doing, because it's a little tedious. I'm not buying what you're selling. Please stop calling here. Sorry, that was so loud. I just assume it was loud because it was loud for me. The momentum before can be broken up into the momentum of the ball, right, before, plus the momentum of the racket before. And that should be equal to the momentum of the ball after plus the momentum of the racket after. Right, this is what I mean when I say it's a little tedious. Because each of these times, right, this m times v has to turn into each of these. So this is going to be the mass of the ball times the velocity of the ball before plus the mass of the racket times the velocity of the racket before. And that should equal the mass of the ball, which doesn't change, velocity of the ball after, plus the mass of the racket times the velocity of the racket after. All right. Now, you should be getting an email. You should have an email that has the 4 graphs that I just showed, and it should have the measurements for the mass of the ball, the mass of the racket that I used, and the mass of the racket that Lily used. They're slightly different. It's funny. I say they're slightly different. They're very different because I held Lily's racket afterwards, and I was like, my goodness, this is light. You'll see from the numbers, the racket that I used was 310 grams. Lily's was 277. So it's less than 40 grams of difference, less than 35 grams of difference. And I thought it was like substantial. I thought it was a stark difference holding it. I told Lily, like, I would probably throw this thing if I was hitting with it. Like I would go through my follow through and just fly out of my hand because it's so light. But that's neither here nor there. But again, I will give you that information because we measured it during class. The racket on a tennis racket actually tells you the mass of the tennis racket, which is very convenient. Now I'm giving you the mass in grams. Please remember to convert it to kilograms. If you needed to run it through a converter, that's fine. If you know the conversion, please do but make sure to do the conversion to kilograms. Otherwise your numbers are going to look all like inflated. They'll look way too big. Now, you'll get numbers here, right? So you'll get some total momentum before, and you'll have a total momentum after, and they're supposed to be the same, but they won't be, right? Whatever number value you get here, if the video analysis was perfect, should be a smaller number than the number you get on this side, right? In order to the percentage that I was talking about, what percentage of momentum was conserved horizontally, what you're going to want to look at is, so this is total momentum after. This is the total momentum before. What you're going to want to do is momentum after divided by momentum before multiplied by 100%, and that will give you the percentage of momentum that is conserved. It's basically like a percent error, right? What percent error did you have? Or what percent error did we calculate here? This is going to be the most tedious part. Please be careful of negatives. Keep negatives in place. Remember that momentum is a vector, so the direction actually matters. The forehand, my forehand hit, and Lily's backhand hit have some negatives involved, so make sure to keep track of those. Make sure to know that those are in place, right? But yeah, keep track. If you are having trouble interpreting or you're not sure which of these boxes corresponds exactly to which of these lines, please let me know. I will absolutely clarify. I will tell you here for the serve, I talked about this box goes with the before, this box goes with racket before, so this box is ball after, this box is racket after. If I look at the forehand, this box here is the ball before, this box here is racket before, and here's ball after, racket after. It looks like the student did a fairly good job separating like before on one side of the screen, after on the other side of the screen. I say that, and here where I'm proven wrong just the tiniest bit. So this box down here is the racket before, and this was where I said there's no information for ball before the serve, so I'd recommend using the information from my serve. It'll be about the same. And then here is ball after, here is racket after. And then again for this one, I have ball before, I have racket before. I have ball after. I have racket after. No, this dude did a very good job of keeping things separate. Now, if you have more questions, if you have more, or if you're looking for more information on how things could have changed, why the answer might be skewed the way that the answers are, please let me know. Like I said, my biggest thing was that we're only taking one axis of data when there are really three axes of data. Another thing is the plotting of the points may have been a little iffy, right? It's kind of dependent on the video quality. So if the video quality wasn't great, then you wouldn't be able to focus on the points as you were trying to place them. Another thing is actually these lines of best fit. Did we choose the correct points to do the line of best fit with? Maybe we should have used different points. Maybe we should have excluded or included more points. So there are a number of reasons that you might have that discrepancy, in addition to just real-life conditions versus ideal conditions. But this should give you the information that you need. Again, these four graphs and the mass of my racket, the mass of Lily's racket, and the mass of the tennis ball will all be in an email that you should have. If you have any more questions, please ask. Otherwise, I'd like this lab. Again, I'll give you until really the end of classes. All right, so June 9th. Do your best on it. Please, seriously, email me if you have questions. I will do my best to answer in a timely fashion. I know that time is a factor here. So, yeah. All right. The next video that I make will probably not be until like just last minute review stuff. A reminder, final is 75 questions. 65 of them count. They're all multiple choice, so you have 10 freebies. Please answer every question. Give yourself the best chance. You'll have your reference table, use a calculator, and yeah, that will be emailed out to you next Friday, June 11th. Yeah. If there's anything else I can do, please let me know. Otherwise, take care of yourselves. Be good. Be safe.